Hello, I'm Alan Fulton, Irrigation and Water Resources Advisor with the University of California Cooperative Extension. I work in the northern Sacramento Valley in the counties of Tehama, Glenn, Colusa, and Shasta. Welcome to this tutorial on using weekly crop ET reports, the gateway to advanced farm water management. This is the final tutorial in a series of several. We have been delivering the weekly crop ET reports to California growers in the Central Valley for several years. The goal of providing these weekly crop ET reports has been to encourage routine thinking about irrigation management. We recognize the importance of water management, and it is our goal to make sure that water management is not the weakest link in the production system. And along the way, we hope that you will discover that on-farm irrigation management can be fun and fascinating, and that it will open your mind and the gate to advanced water management opportunities. Using these weekly ET reports may lead to deeper thinking about water management, questioning and wanting better information along the way. These weekly ET reports bring our attention to the simplest of concepts. We know that as the weather changes and the crop develops, our ET, or evapotranspiration losses, change. We also know that we have different sources of possible water supplies to meet this need. We have stored winter rainfall. We can potentially have capillary movement of water from nearby streams, rivers, and shallow water table. We can have in-season rainfall that occurs. And of course, we can supplement that need for water with our irrigation systems. We also become aware that the performance and maintenance and care of our irrigation systems affect our efficiency at which we can supply that water. As we continue to think about our on-farm water management, we realize that the soils are a factor, the infiltration rates, and how easily we can get water to infiltrate the soils and refill the profile after it has been given a chance to dry down. We also know that different soils have different water holding capacities, and it may affect the depth of the root system of our perennial tree crops. This leads into the question that we know that we're dealing with a long-term perennial tree crop that has the potential of establishing a deep root system that is sometimes hard to quantify. We also know that tree physiology and size of the canopy and other factors affect the irrigation needs and responses of the crop to irrigation. At the end of the day, we're certainly concerned about the practical role and fit of new technology, its cost and its benefits, its ability to pay and return on its investment. In most field situations, applying these weekly ET reports with your knowledge of your irrigation system will help assess the upper limit of the irrigation amount and irrigation run time each week. As you learn, you may want more precision and start down the path of advanced on-farm water management tools. In general, there are three categories of advanced irrigation scheduling tools. One I've described as soil water balance modeling. It originates out of the scientific disciplines of biometeorology, engineering, and plant physiology. The second category is soil water status monitoring. These tools are birthed out of soil science and agronomy and sometimes engineering. And then the third category of advanced irrigation scheduling tools is plant water status monitoring. Horticulture or plant physiology and engineering tend to be the sources of these types of irrigation scheduling tools. It's becoming more and more common to integrate these different approaches, and that's because each of them brings something to the table in terms of strengths of information, and at the same time, they each have their own types of limitations. So let's dive in a little discussion about possible soil water balance modeling tools and their features. Soil water balance modeling tools will often have a geographic information system interface that allows you to incorporate soil maps, field boundaries, and map the location of critical infrastructure and other features. Nearly all soil water balance modeling tools will include applied water records, rainfall, and crop evapotranspiration, the very basic elements of a water balance or water budget. So in a way, you could say that the simple skills that we've been talking about and the simple information we provide in these weekly crop ET reports is the basics of a very, very rudimentary soil water balance management tool. These soil water modeling tools may also include records of fertilizer applications, in particular nitrogen, as nitrogen is very mobile and influenced by our irrigation water management. These soil water balance models may also have record-keeping and reporting capabilities to help us respond to various regulatory reporting requirements. The more sophisticated soil water balance modeling tools will include features that utilize remote sensing, possibly canopy temperature and canopy fraction. They will also possibly include information about crop phenology and elements of nutrient management. There are numerous soil water balance models available, and again, to various levels of sophistication. These are just two examples that I am somewhat familiar with. The first is a soil water balance model called Crop Manage. It has been developed by the University of California Ag and Natural Resources. The lead scientist is Michael Kahn in Monterey County. And another example is a platform called irrigation. This is a platform that I just recently learned about, originates out of the Netherlands, and is finding its way into California. And again, there are numerous soil water balance models out there, and I don't intend to be endorsing any over the other. I simply mention these so you can check them out to get an idea about what they are all about and contain and what their capabilities are. Moving on from the soil water balance models, there is the soil moisture or soil water status monitoring. These are some familiar soil moisture sensors, watermark sensors on the left, capacitance probes on the right. These are familiar sensors that have been in use and currently in use in California and throughout the United States. Currently, monitoring soil water status is the #1 irrigation management tool in terms of the level of adoption. Between 1 in 3 and 1 out of every 2 farmers has reported through various surveys some level of experience and use of soil moisture monitoring tools. So some of the advances in soil water status monitoring that are in focus are the capability to monitor larger volumes of soil and cope better with soil variability and uncertainties about effective root zone. Improve the accuracy in measuring volumetric water content and improve the ease of calibration. There's always the goal of reducing the cost of these sensors, and in particular, the telemetry systems that are involved to remotely acquire the data. And there's more and more interest of integrating soil water status monitoring with soil water balance models. They offer ways to reset the models and verify that the models are working well. And the models offer the ability to verify that the soil moisture status monitoring sites are representative of the larger production areas. Here is an example of work that was being investigated a few years back by Oregon State University, the development and use of fiber optic cables and heat pulses to monitor larger transects and more depths of soil volume. Here you can see on the left, fiber optic cables are installed at different depths. Once they're installed, instruments are used to provide a heat pulse on the fiber optics, and the level of water content in the soil affects the reach of the heat pulse and how fast it travels. And by tracking these patterns, we can begin to graph on the right the soil moisture distribution on a larger volume of soil in an ag production field. Another example is the use of resistivity sensors. Picture on the left shows a crew installing the resistivity sensors, and the right shows some of the results of this particular measurement event. And if you look at the point of the graphic on the right, is just to give you some idea of the scale of which they're trying to monitor soil moisture levels. You can see that the depth is almost 2.4 meters, which puts us close to 8 feet deep, approximately. And you can see the scale across the cross-section is on the order of 20 to 24 meters, or around 60 feet, or in the case of this walnut orchard you see on the left, 3 tree rows wide. So you can see the efforts to really enhance the volume of soil that which we are monitoring. One of the biggest challenges with our current sensors is the small volume of soil that they measure, and getting a good representation both in terms of the effective root zone and both in terms of the spatial distribution of the soils and our soil water distribution, getting good representation. And so this is a thrust of the new efforts. Moving on to the third category, that's advances in tree or plant water status monitoring. Tree and plant water status monitoring can occur at the ground level, be ground-based, either direct remote sensing or indirect remote sensing, and it can be done aerially with aerial remote sensing. So for the moment, the gold standard for monitoring tree or plant water status is the pressure chamber and the use of midday stem water potential in orchard crops. And we use the midday stem water potential measurement, which measures the scaffold xylem in the tree, as highlighted in the red font. The goal is to come up with new technology to replace it that will give us a more continuous measurement and sense of the tree water status, and also be more cost-effective and less labor-intensive. I have recently had the opportunity to work with 2 direct water status sensors, one being a sensor developed by an Israeli company called Saturis. You can see the information here and the website where you can learn more about it. And the other being a sensor called FloraPulse, a company called FloraPulse. You can see the information as well. These sensors are embedded into the xylem tissue of the tree in the cambium, and they measure the very same thing that we measure with the pressure chamber, tree water status or plant water tension. In this case, it is usually placed in the trunk or in one of the larger scaffolds, so it's measuring either trunk or scaffold water tension. Again, much like what we are measuring with midday stem water potential. One of the leading scientists within the University of California working with these sensors is Dr. Ken Shackle at UC Davis, and you can refer to some of his articles here to read more about third-party research and some of the trade magazine articles that describe some of the experiences in the field with these sensors. Here I have, I'm utilizing some data from Dr. Shackle from one of his papers, showing the correlation between stem water potential measured with the PC, the pressure chamber, and the stem water potential measured with, in this case, with the FloraPulse sensor. You can see a pretty good linear correlation. The numbers next to each of these points, I believe, is, if I recall right, is the number of weeks that these sensors have been in operation. This is some data that I was able to observe and was shared with me in French Prune. This is again the floor pulse sensor. This is the average midday stem water potential, these points, the black points, measured with the stem water potential sensor. And this is the daily trends and patterns that we have been observed in this particular orchard. The orange points are the actual measurements measured by a person using a pressure chamber in the field. And so from this example, you can see that there's pretty good agreement. And generally, when we are in the dry down phases and before irrigation, we can see that both are trending down. And in many instances, we can see good agreement on the same day of measurement and the same hour. But on occasion, there is some differences. In general, it appears these sensors are working well enough that we would arrive at the same conclusions, whether we were measuring manually or using these automated sensors. Now, later in the season, and at this particular orchard, this was a situation where water was limited and there was a drought. And even though the trees were becoming more stressed than the farmer might have liked, there just simply wasn't water available to respond and correct it. What we did see in this instance, as the trees got more stressed, there was a greater separation between the sensor and the field measurement with the pressure chamber. This points to there's still work involved to continue to improve these sensors and this type of tool and capability. Another sensor I had an opportunity to work with over the years is the use of a dendrometer. This is also a ground-based, but an indirect measurement of tree water status as opposed to a direct measurement of tree water status. What a dendrometer is doing is measuring the growth of the new year of trunk growth, and it's also measuring the shrink swell within a 24-hour period of the cambium layer and the trunk. It kind of takes us back to when we learned about, as children, about learning about the tree rings, the age tree rings, and learning how that each annual tree ring develops. On average, the annual trunk growth is on the order of about 8,000 microns, or about 1/3 of an inch radius each year. When we zoom in on this data that's monitoring the external rate of trunk growth, we see an upward trend in trunk growth when the tree is not under very much stress. Also, at this higher resolution, we can see periods of greater trunk shrinkage within a 24-hour period between the day and night cycles. The greater trunk shrinkage represents more tree stress on that particular day and correlates with a higher stem water potential measured with a pressure chamber. We can also reach points of stress where we actually see the trunk growth, the rate of trunk growth decline. And because of the tree trunk shrinkage, actually a temporary decrease in trunk radius or diameter. This is a picture on the left of the dendrometer. There is the dendrometer is bolted on. It's actually kind of a wood screw device that holds the dendrometer to the surface of the tree. The dendrometer itself is essentially a plunger that slides in and out and measures the external change in trunk diameter, which is a little bit different, and again, an indirect measurement when compared to the previous sensors that I showed you. Here we are not measuring directly the tree water tension. We are measuring a secondary response. But this secondary response can be correlated with the pressure chamber, and this is what you see here. Two different dendrometers correlated to pressure chamber measurements. And in both instances, you see a good linear relationship between the daily shrink swell reading and our stem water potential measurements. However, each tree can have its own unique response curve. characteristics. This graphic shows the calibrated dendrometer data with our pressure chamber measurement. So we take and predict a pressure chamber measurement based on the amount of shrink swell measured with the dendrometer. And we graph these continuous lines based on the calibration and compare it to the measured points in time. From this experience, we can see that, in fact, we get reasonably good agreement, and we can detect the most stress periods leading up to irrigation, and we can detect the recovery periods after irrigation with the dendrometer, making it a valid, viable tool to help us guide our irrigation management. But again, it is not a direct measure of tree water tension or stem water potential like the other sensors are. Moving away from the ground-based methods, we can look to aerial methods for evaluating tree water stress. We can look to drones, we can look to cameras mounted on the bottom of fixed-wing aircraft, or we can look to satellite imagery. I have been able to get some experience with all three. Drones are a lot of fun to operate, but they tend to be the most costly. Satellites tend to be the most cost-effective, but you do give a little bit on resolution. And the cameras on fixed-wing aircraft seem to fall in the intermediate, in the interim levels. Share with you for a moment a little experience that we've had. This is a almond experiment where we irrigated half-acre plots of almonds for 6 consecutive years at these different percentages of our estimated crop ET based upon our weekly crop ET reports. This was a replicated study. So this is a replicate of 4 plots, a second replicate of 4 plots, third replicate, fourth, fifth, and sixth. This is an image of one flyover on one day. So clearly, the aerial imagery using canopy temperature, we are able to sense and pick out the areas receiving different irrigation management. The theory behind this technique is that as we change our water management, we affect the water stress levels, and this causes stomatal closure. When the stomata on the leaves, on the underside of the leaves close, this reduces transpiration and the cooling of the leaf, which in turn increases leaf temperature. As the stomata close, this also reduces CO2 entry into the tree. So in this instance, the canopy temperature is being expressed and quantified. It's being measured as leaf temperature, but being expressed and quantified as CO2 conductance. These data points, the black, blue, and red, are data points taken from the Tehama County experiment that I just showed you on 3 separate dates in 2015. And the best fit line is this line with the larger hash marks. There is a clear trend and relationship between canopy temperature, stomatal conductance, and measuring stem water potential with a pressure chamber on the ground. As canopy temperature goes up or stomatal conductance goes down, stem water potential or tree water status or stress, the tension becomes more negative or goes up. So there is a clear relationship. However, our ability to predict stem water potential by using an aerial imagery is compromised. You see the scatter is such that we probably cannot get within about a 5-bar estimate on either side of it. This other dashed line on this graphic is the best fit line of work done by a colleague, Blake Sandin, retired farm advisor from Kern County. I just placed this best fit line from the Kern County data just to point out that our response curves in relation to stem water potential are similar. One of the things we've observed with aerial imagery is that we observe a shifting relationship to stem water potential over the season. That relationship between stomatal conductance or canopy temperature and stem water potential is not always the same from one measurement to the next or 1 month to the next. So I'm going to conclude this tutorial coming back to the idea that using the weekly crop ET reports is your first step towards engaging and using more scientific scheduling technology. Hopefully it will intrigue you, bring benefits to your crops, and encourage you to further advance and think about your irrigation management. But as you do this, you're going to experience that irrigation technology is a continuum. It's something that is changing constantly and gradually. There are not clear dividing points. Technologies never seem to totally prove themselves out. They're just constantly in a state of improvement. And there will just be a continuing level of uncertainty. To deal with this, I encourage you to begin with the simpler concepts and technologies, like these weekly reports, and getting your arms around your irrigation system and the maintenance of it and its performance. Move carefully but strategically with trying new technology. Take time to establish benefit, proof of concept, and that it pays for itself. Test your technologies that interest you for robustness, because our agricultural environments tend to be harsh and equipment will be challenged. Try technology on a small or partial scale first and work to expand out. And where it applies, you may choose to start with manual implementation and move towards automation in the long run. So I'm going to conclude now and just say I hope you will continue to try to find ways that irrigation technology and science can help you improve your own farm water management, and that along the way you will have fun with it, because it can certainly be fascinating. Thank you.